Good afternoon, everyone. Thank you so much for your time. I know that you have a real busy schedule, and we'll be with you for about an hour today. My name is Concepcion Molina. Just a little bit of background. I have taught high school math for 14 years, and I've been with CETL for 15 years now. I started off with the Eisenhower Math and Science Consortia, and we did work a lot with schools. But what was interesting is that I've only taught high school, but a lot of the work that we did back then was with elementary and middle schools. So I had a lot of aha moments. I had a lot of opportunity to investigate what you would think is a complex high school topic and trace its roots all the way back down to elementary school. And fortunately, I had some time now to write a lot of those aha moments in this book. And most of today's content does come from the problem with math is English. We do have a pretty sizable audience today, and I know that the title says a chat with the author, but because of the time limitations, we're going to have to limit participation to the chat pods. My contact information will be provided at the end, so feel free if you have some individual questions to ask them later on individually. Today's webinar is being hosted by the Center for High Performing Schools at CETL. If you haven't done so already, please respond to poll 1 regarding your experience with the book, The Problem with Math is English. And by experience, we're pretty much asking you, how much of the book have you read? None, part, or all? And based on the poll results so far, it looks like the majority of you have not read the book at all. So that's good information. Now I'll have a better idea on exactly how to address some of the topics that we'll be talking about today. To set the tone for today's webinar, please go to chat pod 1 and solve the problem that's given to you here. Okay, I see from your responses that some of y'all are really having trouble with this, and there's comments that are pointing to the idea that, hey, what's this vocabulary? I don't understand these words. Typically when you say mathematics, what comes to mind is computation, numbers, those types of things. But I would hope that this is a very good example of, hey, there's a lot more to mathematics than just that. Language. It's an integral part of mathematics, just like any other discipline. Well, like here, what in the world is a gnatpaus? What's an orgle? What's a isvigno? If students do not understand the language of mathematics, the vocabulary, the terminology, they might as well be trying to solve a problem like this, because this is about as much sense as it's going to make to them. Let's look at today's objectives. By the time we finish this webinar, hopefully you'll have a different perspective of the language and symbolism issues that get in the way of developing a conceptual understanding of math. You'll have a better feel for procedural versus conceptual understanding of mathematics. And you'll also get a glimpse of instructional approaches that support conceptual understanding of mathematics. Take a few seconds to look at this old photograph. Think about what learning experiences this little guy might have had. Well, you might have figured out that this little guy is me. This picture is not in the book. I show it to you today to establish that this is part of my qualifications for writing the book. When I first started school, I didn't know any English. We spoke pretty much just Spanish at home. So I had the great opportunity to have to learn English and the content of the different disciplines at the same time, which again was pretty tough because back then there was no bilingual education. But in a way it was also a blessing because for whatever reason I sort of developed a sixth sense for the language. I kind of, just paid a lot of attention to the language and and it's just things that most people don't even notice. Let me just show you a couple of examples of that. Okay, I learned ordinary, I learned what extra meant, and then I had this word. And I figured, well, okay, it's extra and it's ordinary, so we're talking extraordinary. We're talking plain vanilla here. And of course the teacher said, no, Como, that's not what it means. In fact, it means almost the opposite. I said, Miss, but it's extraordinary. Okay, if you say so. Yeah, I learned what a pair of shoes was. I learned pair of socks. And then all of a sudden, pair of pants. I said, okay, wait a minute. There's 2 shoes, there's 2 socks. Where's the other pant? I only see 1. Confusing stuff. Then it really got to be fun in math class. I remember the teacher giving me something like this, and her instructions were, add these numbers up. So what does Como do? He added them up. No, Como, that's not what you do. You don't put it there. You put it down here. You mean I add them down? Okay. Right, you tell me to add them up, but I put the answer down. Well, okay, I'll do what you say, even though it's confusing. This one was a lot of fun, the old goes into. How many times does 4 go into 8? Well, Como being Como, I kind of visualized, I wrote this stuff down, and then, well, I think this is what she means. Well, it looks like it could go in there twice, so I put down 2 for my answer, and I got it right. You know, I thought I was on the right track, but nope, all the other ones I got wrong. The English is confusing. Okay, language and symbolism. Now, a lot of us went through traditional instruction, and you know what we mean by that. It's, the teacher gets up and lecture, you do a bunch of worksheets and all those types of things. Now, the research indicates that teachers tend to teach in the same way that they were taught. But what's neglected is that we don't just tend to teach how we were taught, we're also going to tend to teach what we were taught. And this includes the associated language and symbolism. So we come to the book that I wrote, The Problem with Math is English. Now, one of the things about the title, it makes it sound like it's about English language learners, but it really isn't. It's really about deep understanding of math. It's about conceptual understanding. But it's a different approach because there is a lot of focus on the language and the symbolism that textbooks don't pay much attention to. So let's go to poll number 2, and please answer this. In your experience as a student in K through 12, or in my case 1 through 12, how much did your teachers focus on the language and symbolism of mathematics? And I mean really focus on it, not just a little bit of attention to a definition here and there. Okay, well, it's really no surprise. It looks like almost all of you are saying none and very little. Let's address that. So let's look at this whole issue of the language and the symbolism, which is objective 1. Examine language and symbolism issues that get in the way of developing a conceptual understanding. The problems in math instruction that promote procedural understanding, which is really pretty shallow stuff, and limits conceptual understanding include inattention to language and symbolism, the teacher's tendency to use really careless vocabulary, the use of shortcuts, and the dominant use of naked numbers. I've already shown you a couple of language examples, so let's look at something with the symbolism. Let's say you were asked to solve this problem, number 1. And it might prove to be kind of difficult. Well, let's go to problem number 2. This one's pretty much a piece of cake, right? Some of you might have already figured out that these are in fact the same problem. What makes that first one so tough is that, well, what in the world is all that Greek stuff on there? Well, again, it asks the same question that number 2 does. That's a summation symbol, and it's asking you, well, what's the sum of 2n minus 1 if my n was 1, 2, 3, and 4, which is, again, is exactly what you get with item number 2. What's interesting is that, and it's very frustrating, that in mathematics, we often have mathematics that really is like number 2, but for whatever reason, we make it a lot more complex, and it ends up looking like number 1. Okay, let's look at careless instructional language. As we mentioned before, teachers do have a tendency to use the same terms that were used when they learned the math, and some of it was very careless. Now, this often involves using math terms that have other meanings than standard English. So, for example, carry has a different definition in standard English. Borrow, cancel, one of my favorites. The old 2 goes into 8 again. Bigger half of the cookie, that's interesting. One of these days I want to see what a bigger half looks like. But let's look at E, reduce a fraction. So if you would go to Chatpod 2, what problems might be caused by using that phrase, reduce the fraction? A couple of good comments. I had a comment that just write it smaller. Okay. You might think it means to subtract. Okay. Creates a mental picture of the result being smaller amount of stuff. Okay. But there seems to be, pretty common agreement here that this phrase reduce is, reduce a fraction is going to be problematic. Now, when I was a kid, if I was given a task like this with these instructions, reduce something like 16 over 24, so I went through the process, I did it all, and then of course I figured that 16 over 24 was bigger than 2/3, right? Teacher said, no, they're equal. But miss, I did what you said. I reduced it. I made it smaller. So 16 over 24 is bigger. No, Como, they're equal. So it took some convincing, again, that they are in fact equal. But again, I was fixated on what reduce meant, in plain English, of course. This is something I would ask my students to do, and this is high school. Now, how much sense does this question make? If your kids are interpreting this as asking, how many times does 1/2 go into 10? For the life of me, I can't come up with a model or a real-life context where I would have 1/2 literally going into 10. I just don't get it. Now, it's a whole different story if the kids look at this and the question that they see there is, how many halves are there in 10? Okay, now it makes sense. If I have 10 pizzas, I cut them all in half, I got 20 half pizzas. That makes a lot of sense to me. And this is another thing that we do in mathematics, is that we're so fixated on getting the answer that we don't take too much time to see, well, do the kids understand the question? I know when I was going through school that, they just focus, give me the right answer. I said, well, okay. Shortcuts. Now, you may not think of shortcuts as having anything to do with language, but they really do. The use of shortcuts, it's a problem because the work that you save is more than offset by the understanding that's lost in the process. You really do. Shortcuts really, it's exactly what it says as a shortcut to thinking. Is more, that's what the damage is. Let's look at this example. This was a property that was in an Algebra 1 book that I used. My kids would come up to me and say, well, sir, I've never seen this. I can't figure this out. I can't make any sense of it. So then, of course, you do a numeric example, and they realize they've been doing this for years. But, it's not their fault. Because we let them get away with not doing that middle step, so no wonder they don't recognize it. And then the old infamous, simplifying, reducing a fraction, and typically what we do is the old cancel, and so all of a sudden we get that, and kids are just going through a process. They really don't understand why or anything. Again, it's very shallow, very procedural stuff. Now, as opposed to having them do this, you pretty much start off the same way, but we do this instead. And students need practice with this. They don't realize that these are equivalent expressions, that I can split this up into two separate fractions, 3/4 times 2 over 2. But right here, this next step, that's the key. This whole idea of multiplying by 1, the multiplicative identity, it's such a critical idea in basic algebra because it's the bedrock for solving a lot of equations, to manipulate things around to where you're multiplying by 1. Because now I can drop the 1, and now in this case I end up with just 3 over 4. But it's a lot deeper this way, and the kids really understand what happens throughout the process, why some things go away. I mean, they don't just get canceled. Okay, naked numbers. This refers to our prevalent use of numerals in isolation with no descriptors, units, or context. Okay? This is a problem that I like to give in little slips of paper when we were working with some middle schools. And of course, I think you know what kids would do here. 25 times 28 is more than 24 times 28. How much more? And invariably, most of my experiences were that the students would multiply them all out and then subtract the 2, which is a whole lot of work and really unnecessary. Okay, a lot of times we'll read this as 6 times 7, and don't get me started on this times thing, okay? What we don't do is teach students to interpret numerals as words also, because this is 6 sets of 7, or just 6 sevens. But again, they don't see this times 7 as just the noun 7. So let's go back and look at that problem. What if we change the context just a little bit and say, well, you got 2 farmers, one has 25 cows, the other one has 24 cows. How many more does one farmer have than the other? Well, that's pretty easy. It's 1 more cow. Now, isn't this exactly the same thing with the 28s? You got 25 28s, and that's 1 more 28 than 24 28s. The problem is that the kids don't see this as 25 cows and 24 cows, but you know that's on us. Again, we need to teach them to interpret some of this stuff differently. All right, objective 2. Let's look at procedural versus conceptual understanding. Conceptual understanding deals with comprehension of concepts, operations, and relationships. And it goes way beyond how to. Okay. Now, with conceptual understanding, students are going to know what a concept really is, why it works the way it does, how it connects to other concepts, and what it looks like symbolically and graphically. And also, students will be able to view an idea or a concept from multiple perspectives. They'll be able to make critical connections to other fundamental ideas or topics. And they'll also be able to recognize and understand some of the subtleties in the language and symbolism that they would never catch if they really didn't understand this at a deep level. Well, common sense tells us that the foundation for the understanding of math has to be based on deep, fundamental conceptual definitions of critical concepts. I mean, they have to know what something is. This is something in the book. This is on page 191. Just looking at the process of what has to be involved when kids are going to learn a new term, and not just in mathematics, really, in any discipline. Well, there's probably going to be a formal definition, and that's necessary because they'll probably see this in textbooks and maybe even on some kind of standardized test. But this second piece, definition in their own words, that's a critical one. They have to be able to do this, to internalize it, to really make sense of what something means. But there's going to be terms in mathematics that have different definitions in other disciplines. You're going to need examples and non-examples. They'll need to understand how this idea connects to or is related to others. You might need pictures or symbolism. And they'll also need to know the characteristics, especially also the associated symbolism that goes with it. So teaching vocabulary in mathematics is not as simple as you would think. It's not just, okay, here's the definition, we're done. Okay, the order of operations, that's a good example of how language and conceptual understanding intersect. Most see the order of operations as a convention. It's focused on procedural understanding. But unfortunately, the order of operations, how we treat that is a symptom of what ails us in math education. We tend to focus too much on procedures. Some of y'all have probably seen the acronym, please excuse my dear Aunt Sally, PEMDAS. Well, very quickly, let me tell you a little bit of the background behind this. Way back in the beginning of my CETL career, we were starting a big project with some middle schools, and we polled the teachers to see, well, what are some of the topics that give you or your kids trouble? And the order of operations came up quite a bit. So here comes my boss at the time. He said, okay, Como, this one's on you. You need to develop about a 90-minute training on the order of operations. I said, yeah, right, 90 minutes on please excuse my dear Aunt Sally? Okay, I'll give it a shot. Well, I did a bunch of research and everything, couldn't find anything. And really the question to myself was, so who invented this? Who invented the order of operations? And since I couldn't find any person or team or whatever that laid claim to these rules that tell us the way to do the operations, I figured, well, the answer's got to be in the math itself. So I switched gears, and that's where I looked. And so in developing the training, here's was the key question, actually the key problem. Okay, if you were to give this problem to a bunch of middle school kids that had never seen anything on order of operations, what do you think they're going to do? And in my experiences, almost everybody says, well, they're going to get it wrong. They're just going to work it from left to right. They're going to add 4 and 6, get 10, and then 10 times 5 is 50. And sure enough, if you give that to kids, that's what they're going to do. Okay, well, let's take that problem and let me change it up a little bit. Let's change it to this. How much money would you have if you had 4 pennies and 6 nickels? Okay, let's go to chat pod 3. And so here's your question. Why can the student solve the second correctly but not the first? Okay? And we need to go way beyond, well, they have a context. Well, yeah, but what is it about the context? And here's a hint. 4 plus 3 equals 7. What huge assumption is being made there? Hey, take a couple of minutes and I'll give you all a chance to attempt this. Pretty difficult question, actually. Again, what is it about that second problem? What is it about the context that enables them to do it correctly? Okay, I see some comments like Janice. Y'all are starting to kind of go toward the idea of this adding like items thing. Okay. Okay, so you can't directly add 4 pennies and 6 nickels to figure out how much money that is. Okay. Yeah, I see some comments also about the whole problem with reading left or right. It kind of fixates them on that idea. So, again, why do you think that is, that intuitively something told the kids, I've got to multiply the 6 times 5? I mean, when that happened, when you multiply 6 times 5, what really happens there in the context? What happens to the nickels when you do that 6 times 5? Ah, Janice, bingo, all right. They become pennies. Yeah, now stop and think about that. When you multiply the 6 times 5, that 6 nickels. Yeah, all of a sudden, that's 30, but that's 30 pennies. Okay, now we can add the 30 pennies to the 4 pennies to get our correct response of 34 cents. And again, students just intuitively know that they have to do that with the context. So here's my take on the order of operations. It's all based on this idea that you can only add like items. That's all. If you're going to add or subtract something, it has to be the same stuff. Now we start off real well in kindergarten. 3 ducks plus 2 ducks is 5 ducks. But then we get lazy, okay, or whatever, and that becomes just 3 plus 2 equals 5, the old naked numbers thing. And we lose track of what those things really mean, and we lose track of that huge assumption here that hey, that's the same stuff that we're adding. And what's crazy is that this critical property that you can only add like items, it totally disappears. It gets buried after early elementary, and it doesn't surface again until Algebra 1. Como, you can't add 2x and 3y. They're not like items. Sir, hasn't that always been the case? That's always been the rule. It didn't all of a sudden appear in Algebra 1. So here's the bottom line on order of operations as far as the nuts and bolts. We multiply and divide first in order to determine how many of those same somethings that we have. Then we can add or subtract at the end those same somethings. This is actually chapter 5 in the book, and this is just the nuts and bolts, the basics. I actually go deeper into it, but this is the bottom line. But notice that this would have never occurred to me if I didn't have that focus on the language, and everything, because again, it just wouldn't have clicked. The thing from above or wherever it came from, it wouldn't have happened, again, without this focus on what those numbers mean, what they represent. Okay, here's another scenario for you. Let's go to chat pod 4. Okay, you've taught your kids multiplication of mixed numbers, you use a standard algorithm, but you're tutoring Johnny because he still doesn't get it. Now use 3.5 times 2.5 as the example, and explain how you would show Johnny a little bit more conceptually how to multiply mixed numbers using some other perspective or approach. So just very briefly in this chat pod, just kind of jot down what you might do with Johnny for him to get how to multiply 3.5 times 2.5. Okay, Mary says that she use arrays with whole numbers, start with that, and then translate it and model to solve this problem. Okay. Okay, Michael put it into a real-life context. Okay. Yeah, Heidi's got kind of the same idea. Do sort of a word problem, kind of like we did before with the order of operations scenario. Oh, Michael, an area model. Okay, good. Oh, a different Mary. Oh, and I think I know her. Determine what is 3 groups of 2.5. Okay, and then address the half of 2.5. Okay, good deal. And Marita says related to money. Yeah, that would work. Okay. All right. Good ideas. Some good different strategies and approaches. And y'all pretty much have touched on some of the things that I did in Chapter 8 of the book. Chapter 8 is about operations with fractions. Chapter 7 is about fractions as a concept, which I titled Fractions, the F word in mathematics, which, hey, I'm telling the truth. That's been my experience anyway. Now, one approach is what I would call the numeracy approach, which is just basically what multiplication is. If we think of 3 times 2 as 3 groups of 2, then 3.5 times 2.5 would be 3.5 groups of 2.5 each. Now, of course, I've got more circles than I need here, but we need them in order to see where the fractions come from. So I don't need sets of 3, I need sets of 2.5. So that's how come I have the vertical line, so I can have groups of 2.5. And then I don't want 4 groups of 2.5. I want 3.5. So I got 3 sets, and I only need half of this one, so that's the horizontal line. And so there we are. And now just by counting, the kids can figure out, well, let's see, I got 1, 2, 3, 4, 5, 6. There's 2 halves, there's 7. There's 2 halves, that's 8.5, and a quarter more, that's 8 3/4. So no changing to improper fractions, no multiplying numerators and denominators, none of that. Yeah. Now, of course, people will say, well, Como, you can't do this all the time. What if you had 67 and 3/16 times 24 and 10/11? Well, yeah, obviously, that's not going to work, but still, kids have got to have a foundation. They've got to see exactly what happens. And yes, when you get to more complex numbers, it would be hard to do it visually, but they can still visualize it in their head and understand what's happening with the process. The area model is very much related to it. And again, let's go with a 4×3 example here, because again, we need them to see where the fractions come from. And it's the same basic idea. 3.5 sets of 2.5. So again, there's 1, 2, 3, 4, 5, 6. There's 7 with those 2 halves. There's 8.5, 8 3/4. Now here's where it gets to be really fun. This is the algebraic approach using the distributive property, where we split the 3.5 to 3 plus 1/2, which sometimes is hard for kids to see, believe it or not. And that 2.5 is 2 plus 1/2. So when you have your partial products, now look at the beauty of all these connections. I've got 3 groups of 2. Well, here they are with the area model. Here they are with the numeracy model. I got 3 sets of 1/2. There's my 3 halves, and here's my 3 halves over here. 1/2 times 2, well, it's better to think of that as 2 1/2s. So here they are here in my area model, and here's 2 1/2s over here in the numeracy model. And then, of course, we have our 1/2 of 1/2, which is the 1/4. So again, a lot of nice connections, and again, it gives the students a lot, different things to think about. And again, it's the connections here where they can really start putting 2 and 2 together, literally. Now, let's think about the standard algorithm. I know when I was growing up and I was taught this, okay, change it to improper fractions, multiply numerators and denominators, and you get 35/4. But that's kind of where it stopped, so I never really understood, well, what's the 35/4? Well, that's really 35 times 1/4. I can represent it symbolically, but that's 35/1/4. But that's still not the whole story, because I still don't get, well, what's the 1/4? Well, if you look at the 1/1 square, and you look at the 1/4, well, look what you really have. You've got 35 of these little rascals, okay? And they're all these square units, but each of these is 1/4 the area of a unit square, a 1×1 square. Okay, now it makes sense when I understand exactly, well, 35 what? What are these 1/4? So what happens in this context, the multiplication, that process is where the linear units that you started off with get converted to square units, okay? Because over here, the 2's and the denominators, that's really like 1/2 inch by 1/2 inch, and you end up with 1/4 of a square inch. Okay, students can also recognize subtleties if they really have a conceptual understanding. All right, consider this equation, 1/2 equals 2/4. Is that true or false? And that is a problem that I pose in the book. Well, of course, as adults, we're going to say, well, that's true. But let's say you're teaching a class and you have a little Como in there, and he's bouncing around, raising his hand, miss, I know what it is, I know what it is. That's false, okay? And I can show you. Look, I show you. Here's my pizza, and I'm going to get half of it. You're the teacher, so you get a bigger pizza, but you cut it into 4 pieces, because that would be a huge half of a piece. So now, you're trying to tell me that the pizza I'm going to get is the same amount as the pizza you're going to get? I don't think so. So that's false. Okay, I showed you, I proved it. So what are you going to do with that kid? Send him out of class, I don't know. Okay, well, look at the representation of a fraction, some number A over B. Now, I'm sorry, but as a representation of quantity, that is and always it will be an incomplete expression, okay? I mean, here's what I mean. What's the exact value of this? How much is 1/2? I mean, really, can you give me the exact amount? Is it 20? Is it 35.5? I mean, how much is 1/2? Right? Because you're missing, well, what's the whole, right? So, how can you express an actual amount with just that piece? Again, it's incomplete. But como, I mean, no, I'm sorry, that's true. Because we assume that you're talking about the same whole or the same size whole, right? But where in the symbolism, what does that tell us? We're kind of stuck like with that 4 + 3 = 7. We have to make all these assumptions, and this is math. I thought this has to be pretty precise stuff, and here we are making all these assumptions. Well, my take on this is how I would make that true. I would change it and stick in this variable. Now I've eliminated that assumption. Now I do in fact have the same whole or the same size whole for each. Now definitively that's true because now I know what the exact quantities are on each side. Well, guess what? Como has a cousin, Conchita, and she's jumping up and down and raising her hand, and she finally gets called on, and she says, well, Miss, I think it's false too, but my cousin, he doesn't have it right. Let me show you why. This is how come it's false. Okay, here's 1/2. I got 1 star and 2 pentagons. Okay, and here's my 2/4. I got 2 stars and 4 pentagons. Now remember you did that thing with the balance scale, and you told us that it had to balance out, that you had to, in order for the equation to be true. Well, Miss, look, you have a whole bunch more stuff on the right hand side, so it's going to tilt over that way. So no way that you don't have the same amount on each side. So that's false. Oh boy, why do I have such kids in my class, right? All right, okay. She's saying this is false, and she's kind of got me over a barrel here. But then I have to stop and think. One of the things that I do in Chapter 7 is I talk about something called the fraction kingdom. Because what a fraction means is dependent on the context. And what's crazy is that we use the same symbol to represent every single type of fraction, and it can get very confusing. So kids have got to understand where they are. I mean, it's kind of like geography. If you're in the Amazon, the kids know that they're not going to see polar bears. Okay, so that's the exact same thing here. Okay, I'm not going to see a polar bear here, because here what I've got is, this is about relationships. Okay, these are ratios. Okay, this is a ratio context for this fraction, which makes this equation a proportion. And what's interesting now is that now I've got to adjust my interpretation of the equal sign, because the equal sign is typically about quantities, but not here. It's about relationships. So now what this is saying is that this relationship over here is equivalent to this relationship over here. For every 1 star, I've got 2 pentagons. So again, very important that kids know where they are so that they'll know exactly how to interpret these things. So now, knowing that I'm dealing with relationships with ratios here, okay, now I can see why it's true. Okay, let's take a quick look at Objective 3, some instructional approaches. Well, teaching for conceptual understanding has to focus on understanding the whats of concepts and the whys of the processes and the theorems and the properties. But of course, we have to pay attention to the how-tos, because, I mean, that's what's tested. So what does teaching conceptually look like? Well, here's my take. We've already done this. You've got to focus on the language and the symbolism. Must. Simplify yet deepen is an overarching philosophy and approach. That seems kind of contradictory, but it is definitely very doable. In fact, that's the only way that I can deepen my own understanding is to simplify it. Because again, I'm not a math genius. I'm not a mathematician. I'm a math educator. There's a whole lot of difference. Mathematician, I am not. They always look for and use connections among mathematical concepts. There's so many concepts that are linked to each other, and in fact, when they learn one concept, they've actually learned part of another, and so you're making the task a lot easier because they already know part of what's coming up with the next topic. So real important to do this. Continually lay the foundation for future topics or concepts. I mean, you don't have to use the terminology. For example, you can teach fourth graders what pi is. You don't have to say it's pi. You can just do some hands-on activities, and they'll figure out for themselves that, oh, it's about 3 times further around a circle than it is straight across. Okay, so they have a conceptual understanding of pi, even though they don't know the word yet. And in fact, they understand pi better than probably some kids in calculus class. And approach math as relationships. A long time ago, I saw an adage. I can't remember who to give the credit to, but it said that arithmetic is about computation, mathematics is about relationships. And when I really took that to heart, gosh, you talk about some aha moments. So that's a huge idea. Again, to treat math as relationships. We won't have time to go through all of these. So let's just focus on number 1. Let me show you a couple of examples there because that's what we've been really zeroing in on anyways. Language and symbolism. Okay, what if I came up to you and told you this? You'd probably think I was some kind of strange cookie. Now what do you think? Hopefully that would change your perception of me. Oh, and by the way, I'm not that good a fisherman. We happened to hire a guide that day. So it's really, really important to be aware of the context and circumstances of how language and symbolism are being used. So real quickly, let's look at instructional language. What would be the impact? So let's go to Chatbot 5, and how would you compute these two, that top addition problem and then the bottom multiplication one? How would you add those mixed numbers, and how would you multiply those whole numbers? Okay, I'm starting to see that some of y'all think that, hey, I shouldn't work them the way that they sit, doing them left to right. There's an easier way. Yep. Yeah, like Kelly added the 4 2/3 and the 6 1/3 first, and then the 3 1/7. That makes sense. Yeah, Michael says rearrange them. Yep. Yeah, so y'all are thinking exactly what I was thinking. But if we look at that addition problem, and I remember back as a kid, and they taught me this order of operation stuff. I was told, okay, you're deciding between adding and subtracting or between dividing and multiplying. There's no grouping symbols, so you do it from left to right. So what do? I work it from left to right. I go through all that hassle, common denominators, the whole works. And of course, here comes the teacher and says, oh, come on, you didn't have to do it that way. You could have, switched the order around. It's a lot easier to add 4 2/3 and 6 1/3 and then the 3 1/7. You don't have to do that common denominator stuff. Well, but miss, the rule says there's no grouping symbols, so I do it from left to right. So I've kind of done the students a disservice because they're doing exactly what they were told to do. So no, I better restate this and maybe add on something like this, that, this is how you do it, unless, there's some mathematical property that allows you to do it in an easier or more efficient way. So again, sometimes even the little thing like this where you leave out something really matters. Okay, another couple of examples. I talk about language impediments, and one of them is ambiguity. There's some words where the meaning is kind of ambiguous. So like this first example, let's say you're going to teach similarity. you should ask this question at the very beginning, and you're going to get responses based on their idea of what similar is in plain English. But then you go through the unit, you teach similarity, and then you ask this again at the end, and you'll get different answers because now they're going to answer based on the mathematical idea of similar. So again, it'll really help them to see the distinction and the importance of understanding, the multiple meanings of some words that they run into in mathematics. The second one is one of my favorite problems. I like to take a problem like this that it's pretty simple, but it really investigates a big topic, like in this case, proportional reasoning. And I would give this across several grade levels to see where the kids are. And so if you have a bunch of 8th graders that are saying, well, it's the older pig grew more because 8 pounds is more than 5 pounds. So you've got a huge problem because, proportional reasoning is a big idea in middle school. And they haven't transitioned over to realize that, hey, wait a minute, a different perspective here is that, wait, the little pig grew more because 5 pounds to 10 pounds, it doubled in weight. And that bigger pig just grew by 8%, 8 pounds, out of 100. So again, here though, the ambiguity is with the word more. But students have got to see this from both perspectives. Now, sometimes there's things that you can use to teach conceptually, and you think that it's some of the same old, like drill and practice. But if you do it in a clever way, like look at this first example. Let's see, 24 divided by 2, that's 12 divided by 3, that's 4. Then the second one, that's 8 divided by 2, that's 4. So, hey, wait a minute. I get the same answer, but you're dividing. I thought division wasn't commutative. What's the deal here? So, again, this would really generate some discussion and some investigation, and they would learn to discover, something new, even though it was what you would think just drill and practice. But the real power and tremendous advantage of teaching conceptually is to connect and leverage different concepts, properties, and strategies. Now, let me just show you a quick example. Don't you just hate this? They start adding fractions and they add the numerators and the denominators. Okay, well, let's go back. And this doesn't happen in the space of a week. This has to happen over several grade levels. You continually use that idea of combining like items, and I never said that shortcuts couldn't be good. You can use shortcuts wisely, and then we can combine that to help us with the fractions. So, wait a minute, forget this naked number stuff. You've got to, again, push on combining like items. So make them write it out. I mean, you're integrating math and English. You want them to learn how to recognize and spell the words, so do stuff like this. 4 dogs and 2 dogs is 6 dogs. And they'll know that, hey, I can't add 4 cats and 2 dogs. Now, shortcuts. Oh, sir, we've been adding this, and we've been writing dogs, and I know how to spell it. I know what it looks like. Cut me some slack. Okay, I'll tell you what. I'll let you do this. I'll let you do D for dogs, all right? Well, look, the algebra teacher is going to love you. You're already establishing the idea of variables, that you can add 4D and 2D and get 6D, and that you can't add 4C and 2D. Now we can connect this to fractions. Look, same deal. 4 fifths and 2 fifths is 6 fifths, just like 4 dogs and 2 dogs is 6 dogs. Oop, and I can't add cats and dogs, so I can't add fifths and thirds either. And then when they see it symbolically, hopefully they'll make the connection that, hey, this won't work, can't do it. Now the benefits here is that you're continually reinforcing the idea of combining like items, combining like items, and you're applying it to fractions. But here's an important one. You're reinforcing this idea that adding and subtracting will not change the units. If you add cats and cats, you're still going to get cats. If you add fifths and fifths, you're still going to get fifths. And you also address the measurement strand. Measurement isn't just about feet and inches and millimeters, okay? It's also about cats and dogs and fifths, okay? Because any number is going to represent something, which does deal with measurement, okay? And that's one of the weak areas that we always have as far as student performance. hopefully today's webinar has raised your awareness of the problems created by the language and symbolism of math, and you have a feel for the depth of understanding that we should all try to instill in our students. The content that we covered today is pretty much representative of the book's content overall. And that's really the only book or whatever that we referenced today was the book, and here's how you would cite it. As far as resources, if you have not purchased the book, and I noticed that several of you hadn't, you can access it through our website, and here's the address, but don't worry about writing it down because we'll give you the link in a little bit. And this is what the page would look like. If you were to go here underneath the picture of the book cover, there's a direct link to Amazon. What's nice is that they priced the book very reasonably. Right now at Amazon, I believe it's right under $22. CETL does offer professional development opportunities through the Center for High Performing Schools. Here's the address and the main page on our CETL website for the Center for High Performing Schools. And this is what the main page would look like, but if you went to the bar on the left, and if you hit the link for mathematics, it would take you to our math offerings. Now, in the near future, today's webinar is going to be on this website. So again, we're going to archive it. I'm not sure how soon it'll go up, but it usually doesn't take too long. And as far as the contents of the rest of the page, it gives examples of some of the conference presentations, some of the topics that we've given, but it also gives you an idea of what we could offer as far as professional development. Of course, we can always customize professional development to fit whatever your school or district needs are. So CETL does rent me out. Okay, so here's the resource information for the book and for the Center for High Performing Schools. And then lastly, here's my contact information. And I really mean this, folks. Please feel free to contact me. I know, again, that we didn't have any time here at the end to address questions or anything because the hour is up. But again, if you have individual questions, you want to talk about, some math problems, something that you've had trouble with, again, just email me or give me a call. That number is a direct line to my office. So again, feel free to contact me. I love to talk math. I love to do this because, and I love to go to schools and work with teachers because invariably I always learn as much as the teachers do. Because I either learn something new or I pick up a new challenge to really look at it and try to make better. Oh, and lastly, sometimes we get asked for the copies of the PowerPoint. What I can do is please email me or call me, and I can, if you really want it, I can get you a PDF. So again, just send me an individual request if you want the PDF for this. Again, thank you so much for being here today. Hope you enjoyed it, and again, feel free to contact me. I'm usually here. Once in a while they send me on the road, but I'm typically here. Thank you all very much.